As chairman, Professor Fujita organized a one-day international symposium in New Delhi, just before the 13th International Conference. This was an outstanding success, bringing together specialists in underground construction from many countries. Following the success of Professor Fujita's initiative, it was decided to initiate a series of two-day international symposia on geotechnical aspects of underground construction in soft ground, with a third day devoted to technical site visits to underground construction projects. This international symposium has been held every 3 years over the past 10 years, as follows: 96 in London, 99 in Tokyo, 2002 Toulouse, 2005 Amsterdam, 2008 Shanghai. For each of these international symposiums, there has been a wealth of information published in the proceedings, with many hundreds of papers published on a wide variety of underground construction topics of major technical interest, mainly on case histories and new research. Professor Fujita was the inspiration for this highly successful international symposium, and we all owe him a great debt of gratitude. At the next international symposium in May 2011, to be held in Rome, this was written in 2010, we will fondly remember Professor Fujita as the father of TC28 and a great inspiration to us all. It will be proposed that a prestigious lecture in memory of Professor Fujita, to be named the Keiichi Fujita Lecture, will be delivered at each subsequent international symposium on geotechnical aspects of underground construction in soft ground. The Fujita Lecture will be a lasting tribute to Professor Fujita's remarkable contributions. Professor Fujita's wisdom and experience, combined with extraordinary energy and a great sense of humor, will be sorely missed. Those have been the words of Professor Robert Meyer in September 2010, and this is a full explanation why we are here today to listen to a Fujita lecture by Professor Hirokazu Akagi. It's not a coincidence that Professor Fujita and Professor Akagi are both from the Japanese society or the Japanese community. Certainly this is due to the excellency of the geotechnical aspects and work done at Japan, and the society, the Japanese society, is one of the most active and of the societies existing. Professor Fujita was born in Japan. He was educated at the Waseda University. He is a lecturer at is an associated professor and professor of Waseda University, a visiting researcher of University of Canterbury. He is a board member and vice chairman of the Tunnel Engineering Committee of the Japanese Society, general reporter for some international conference, and he has many research topics. And I would like to invite Professor Akagi to deliver his presentation.
Thank you, Mr. Chairman. I'm Hirokazu Akagi, and I'm coming from Waseda University, Tokyo, Japan. And also, I'm one of the core members of TC204, IWSMG, and also representing Japanese Geotechnical Society, I should here. And already explained by the chairman, and I'll show you what is which lecture. These are the lists of honor lectures of IWSMG, and which is updated on last year. So TC is Technical Committee of the International Society, has honor lectures. For example, TC 101, which is on laboratory testing. They have the Bishop lecture mentioned here. And also site investigation, TC 102 has Mitchell, and TC 104 has Schofield lecture, and TC 104, unsaturated solids has Blight lecture, and TC 202 Doctor lecture, and TC 203 Aswick has Mitchell lecture, and also our TC 204 has the Mitchell lecture mentioned here. And also Chodrotario and McLellan, Menard, Lowe, Kinisal, Lacasse, Baran. Very distinguished names are here. And this is a picture of late Professor Keiji Fujita. And he died 2010. And as explained by the chair, he was quite active, and this picture shows the special lecture B given by him, and on the underground construction, tunnel, underground transportation at the 12th IC International Conference, Solutions Foundation at Rio de Janeiro, Brazil, August 1989. And also in 1994, he has done the state of the art report on soft ground tunneling and various structures at the 30th International Conference, SMFE, in New Delhi, India. And the same year, TC28, now TC204, has the first symposium was held in New Delhi. And this picture shows one of his hobby was to play golf, and we shot at his competition. And the first lecture was done at ISO 2014. And lecturer was Professor Hugh D. St. John, Geotechnical Consulting Group, DCZ, UK. The title of his lecture is Urban Development, Decision-Making Processes in the Planning of Substructure Construction. And the title of my lecture, the second lecture, is Amazing Underground Construction Technology in Japan. And this slide shows the contents of my lecture. The first chapter, I show you some simple introduction of my lecture, and I'll cover 6 big projects which are done mostly in Eastern Japan. The first project is large shrine cave and the MAODC project. MAODC means Metropolitan Area Outer Discharge Channel Tunnel Project. And the third chapter, I will show you Seal Tunnel Enlargement Method, STEM, for the underground expressway. The fourth is the construction of Tokyo Outer Ring Road, which is named as Gaikan. And also, fifth topic is on Chuo Shinkansen construction plan by Maghreb Linear. And sixth, the salted JR and the salted Tokyo through lines. As the seventh topic, is subway Tozai line, Yamisamachi Station, innovation plan, platform, and track addition. And finally, I'll show some summary. And for this second lecture, JGS, Japanese Geotechnical Society, has organized the special committee to prepare this lecture. Professor Mr. Gasimoto and Dr. Kiyamutsuno and Mr. Satoshi Honda and Mr. Hiro Komatsu and Mr. Satoshi Sakata and Red Card on Dr. Shinji Konishi and Mr. Katsushi Komoto and Mr. Koji Funahashi and Mr. Takeo Sasahara and Mr. Kohei Yamazaki and Dr. Yoshi Tobashi deeply acknowledged. And also, I have to show the special thanks to Dr. Arsenio Negro for his support. And as an introduction, I'll show you the MODC is here, Tokyo is here, Tokyo Bay is here, and the south state seal tonics expansion method, and for Gaikan is here, and fifth, Chiyo Shinkansen linear is going from Shinagawa to Nagoya, and sixth one is use sense method, which is used to build the new train network, and the seventh one is the innovation of existing subway station by the Tokyo Metro. I show here all the topics is focused on Eastern Japan around Tokyo. As a chapter 2, I show large underground shrine cave and the MAODC project. What is MODC? Metropolitan Area Outer Underground Discharge Channel, used for the flood water escape to save Tokyo area. This line shows the discharge tunnel. In other words, this is underground river which escapes the flood water to save Tokyo area. And this figure 2 shows the bird's view of MAODC, view from this direction. That's why the flood water is coming from the right-hand side to the left-hand side. And this slide shows the magnification of the MAODC. And this underground river was constructed from March 1993 to June 2006, almost 10 years ago. And there are 5 big shafts, which is named as bank. And these 5 banks are connected by the seal-driven tunnel, and flood water is coming from west to east, and the flood water is discharged to this river, Edogawa. And these tables show the specification of the shaft bank and also the tunnel which connects these shafts. And banks are the storage spaces for flood water, and the inter diameter is around 30 meters shown here, and the depth is around 72 meters from the ground surface. Quite large and deep shaft. And also seal tunnels has the diameter is around 10.6 meters, and extension is 1.4 kilometers and almost 2 kilometers, as shown here. And seal tunnels are connected to the flood water storage banks. And this picture shows the bank shaft, deep around 70 meter depth and large diameter, and the 30 meter diameter have been built by using the inverted lining method, the top to bottom excavation as shown here, using the quite thick wall, thick diaphragm wall method. And this slide shows the large diameter, around 12-meter slurry CTBM was employed, and special concrete segments have been easily and rigidly connected by the push and bonding connectors, and which reduces the construction period as shown here. And particularly this picture is quite famous one, which is like large banks are famous for the huge underground space as the underground shrine, attracting many tourists as Turkish basilica system. And actually this MAODC reduces the flood damage resulting from the maximum rainfall once in every 10 years, that is 270 millimeter rainfall in 48 hours. And this chapter I shows the seal tunnel enlargement method, STEM, for the underground expressway. The reason why this method was created to avoid the disturbance at the ground surface and to utilize the highly developed urban area and to achieve a good urban service landscape. And that's why utilization of underground space is a social requirement to create infrastructures such as expressways. This picture shows the underground space near Shibuya. Shibuya is one of the big cities within Tokyo area. And this map shows the expressway around Tokyo area. So there are 3 ring roads as shown here, and also some radial expressway as shown here. And Metropolitan Express Company is responsible to build the ring road named Gaikan. Sorry, expressway. And this figure shows the seal tunneling enlargement method, STM. And this figure shows the structural feature of the connection between main tunnel is here, car drive is here, and also in the case of expressway, we need to diverting and merging section as shown here. So main tunnel is used for the trunk line, and this pink colored one is another. So this tunnel is used for the merging traffic from the ground surface to the main line, and also many line is going through this direction, and that's why when the diverting traffic is going up through this tunnel, as shown here. And tunnel is quite large diameter, 12 meters and 30 millimeters, and also the shape of the cross section is changing with depth. That's why that is a quite complicated structure in longitudinal direction, and also there's no column as a connection. And what is the seal tunnel enlargement method? In order to build the merging and diverging section of expressway, tunnels such as an entrance and an exit to the expressway. And as a first step, main seal tunnels are constructed as shown here by the seal TBM. And the second step is the third ground between main seal tunnel and here would be excavated, and the rampway tunnel would be built to connect the main seal tunnel actually here. And this figure shows the technology for seal tunnel enlargement method, which is using the cut and cover method. So this green circle shows the main seal tunnel, and from the ground surface, the excavation is done to connect the main seal tunnels. And then, after the construction, the backfilling is done, as shown here. And this picture shows the connection between main seal tunnel and lamp tunnel, as shown here. Main girder of the main steel segment is embedded into the RC body, as shown here. And also axial force is transferred by the shear connectors of the ribs on main girder, as shown here. And I'll show you another method with full trenchless method, and which means without any cut and cover method. This red colored one shows the lamp launching shaft. The first, the lower lamp tunnel was built. And second, the upper lamp tunnel was built, as shown here. Then, main seal tunnel are built, as shown here. And we need to connect these main tunnel and lamp tunnels. And without any cut and cover method, we built the connection section, as shown here, within the tunnel. And this figure shows the outline, the step of seal tunnel enlargement method with trenchless method without cut and cover. The first figure, as shown here, main tunnel is here and lamp tunnel is here. And then excavation of upper half, as shown here, by mountain tunnel method with top steel segment, as shown here. Then the excavation of lower half by mountain tunnel method with bottom steel support. And excavation of middle portion and removal of the lamp tunnel and main tunnel segment. And lower part is also removed, completion of the connection. And finally, the completion image as shown here. And this slide shows the actual construction site of seal tunnel enlargement construction at top section, this section. And excavation of upper half by mountain tunnel method. Mountain tunnel method means there's no support of the face. And installing the top steel segment is shown here. And next slide shows the bottom section, excavation of lower half by tunnel method, mountain tunnel method. And this one should be main seal tunnel, and also this one is small diameter lamp tunnel. And in order to use this mountain tunnel method without any support to the face, we have done the 3D final device method analysis using flag for verification. So this is the finite difference method analysis model are shown here. And tunnel is here. And this slide shows the 3D finite difference method analysis results. And the blue color shows the elastic region. That's why the surface is stable interface support. The elastic space down and interface of upper half transportation like each construction steps. And no need to carry out to do some sort of improvement to stabilize the face. And also no leakage, water leakage and cracks of the face. And because the third condition is quite thick soil layer named as casing, with self-supporting and homogeneous as expected. And also there's no groundwater leakage in this case. And this picture shows the distribution of safety factor, which was obtained by the flag. And safety factor for flags is calculated by 1 coulomb yield criterion, and the safety factor is more than 1.0 in the entire area around tunnel, including center pillar. That's why we decide, so no need to carry out for improvement. At the fourth chapter, I will show you the construction of the Tokyo outer ring road named as Gaikan. And this is the transportation network with 3 ring roads, and this is central Tokyo, and 9 larger roads around Tokyo. The plan, this original plan, was published in 1963. And ring road construction has been delayed compared with radial roads. And the central circular road opened just two years ago. And Tokyo outer ring road, this one, second ring, is around 40% open, and also most external outer ring road is named Kenmo Expressway, and around 80% open. In total, for the ring road, 70% has been open already. And I'll show you 2 case records for this Tokyo outer ring road. And this road is one of the 3 roads with Kenmo Expressway and Central Circular Route. And the 34-kilometer long section between Misato, Minami, and Oizumi. Misato, Minami is here, and Oizumi is here, has already opened to public. And the 60-kilometer section between Kanyetsu Expressway and here, Kanyetsu Expressway, and Tomei Expressway is here, is under construction. And this expressway is built under the first deep underground road construction. And we have the special law in Japan. And what is the special law? This figure shows the content of the special law. If the bearing soil layer is smaller than 40 meters, in that case, the deep underground is 40 meters or greater than 14 meters is named as deep underground. And if the bearing layer is greater than 14 meters, in that case, deep underground is just 10 meters below the surface of the bearing layer. And these deep underground space can be used for the public use without any compensation pay for the owners. So that's why we'll be able to build the underground construction cheaper than before. And in this Gaikan road, this picture shows the longitudinal view of the Gaikan expressway. And this blue colored one shows the areas that have been approved to develop under the Law Act, blue line, around 40.2 kilometers. And the junction is shallower than 14 meters. That's why in this area we have to pay some compensation to the owners. And another, this slide shows the segment Kanye Expressway and to Tomei Expressway. And this is the overview of the project, which is around 40 meters and 98 meters. And the lines, number of lines are 6 lines. And proponent is National Expressway, Eastern National Expressway Company, and also Central National Expressway Company. And this slide shows the geological features along the route. The substratum along the tunnel is very steep clay, named as Kazusa Sodu. And from Tomei Junction to Oizumi Junction, the geological condition includes the coastal layer, Kitatama layer, and sand layer, and alternation of strata containing pebble, sand, and coastal layer, and which is inclined to the north. And the soil condition is quite similar to the Metropolitan Expressway, as I mentioned before. But in this case, the groundwater is expected to leak. That's why, in this case, we have to be careful of the soil stability to adopting the mountain tunneling method. And the seal tunnel diameter is the largest one. Construction by the 60-meter diameter EPB type sheet machine is planned to be used. And the southbound tunnel and northbound tunnel will switch their position to this position. And 4 TBM will be joined on this here. So we have to connect 4 machines within the soil. That's why we need to be careful to build this connection. And also, we need to enlarge for the diverging or merging at the entrance or the exit of the highway. And so in this case, in order to ensure safety during construction and the long-term stability, and the company is planned to basically circular geometry shape will be adopted, which is able to provide sufficiently wide zone of water capture performance, as shown here. And so we need to keep quite high water tightness. That's why at present, I think we need to use soil freezing method to build underground space enlargement. And the next topic is on segment of Misato Minami to Koya Junction, this section. And at this section, Tokyo Gaikan Expressway construction crossing JR Japan Railway Soul line between Ichikawa Station and Moto Yawata Station. Ichikawa Station is left and Moto Yawata Station is right, as shown here. And Gaikan Expressway is going through this section. So that's why we need to build the intersection to JR subline. And this slide shows the complete image view and constructs a double layer space of the General National Way and the Tokyo Gaikan Expressway. The top of the General National Highway is here, and also in the underground, Tokyo Gaikan Expressway is going through the underground. And the railway viaduct, JR line is here, where commuting trains and the night express trains are running every few minutes. That's why we need to extend the current viaduct span. So extend viaduct span more than 2 times compared with the current span. This is a completed section. So we need to build the new red-colored box and pillar and girder structures. So 2 techniques are adopted: extend the existing RC viaduct span and replace the girder, and construct the underground box culvert, which is shown here. Step 1 is a box culvert within ground by using a pneumatic caisson method as shown here. And this is the measurement result of the displacement of the existing railway track. And step 2 shows the new piers of the viaduct and place the new continuous girder as shown here, and connecting the piers and new girders as shown here. And also, after completion, weight replacement is done by using the hydraulic jacks as shown here. So there are lots of jacks, hydraulic jacks were used to replace the weight to the new piers. And this picture shows the before replacement and this one and after replacement. And the 5th chapter covers the Chuo Shinkansen concept plan by maglev linear. This picture shows the test run of maglev linear train. It's a Tokyo area. Shinagawa is the starting station, Shinagawa to Nagoya. And finally, Nagoya to Osaka is planned to be connected by the maglev linear train. And this black line shows the existing Tokaido Shinkansen, which is 300 km per hour service, and we need to substitution and innovation of this existing Tokaido Shinkansen line by using Chiyo Shinkansen line, which is planned to be used as 5 km per hour. And this figure shows the longitudinal route profile. Extension is around 286 kilometers. Tunnel is 246 kilometers. And going through the Japanese Southern Alps and Central Alps mountains. The maximum cover is around 1,400 meters, as 25 kilometers long. And Shinagawa area and Nagoya area will be employed. 86%. And this is the cross-section of mountain tunnel and sea tunnel. And this construction is just starting and to be completed in 2027 to Nagoya and in 2045 to Osaka. And 6 is the Sotes JR and Sotes Tokyo through lines. Sotes is a private train company, and Sotes is connected to JR, Japan Railway line, and then Sotes to Tokyo is another private train company. So these lines connects the Sotes train is going into the central Tokyo. And in this project, SENSE is used. SENSE is an acronym, seal tunneling method, and extruded computer learning, a new oscillator tunneling method system in the SENSE. And this method was used to build the Tohoku Shinkansen and Hokkaido Shinkansen 2008 and 2012. And for this line, the new Nishiya Tunnel and Hada Tunnel will be built by using this SENSE method. What is SENSE? The phase stability is kept by the closed phase EPD type single TBM. And the phase injected behind the button. After and the stability of the button, the second line with the function of the couple is placed in the area. So this picture shows how these two line is built. So TBM is going through the left direction, and inner forms are disassembled and assembled in a TBM tail as shown here. And this is the primary shotcrete or flesh concrete is injected to the boiler behind the machine. And this picture shows actual SENSE machines. And the first Nishiya tunnel was already completed. And the measured result shows the better control of the displacement during the TBM driving. And also, new Hazard tunnel is now under construction. And the 7th chapter shows the subway Tozai line, Minami-Tsunama Station innovation. This Tozai line is quite old subway line. The length is around 30 kilometers. And so it started in 1969, 50 years ago. And the ridership is including shown here. And also, the Inamisama station is existing within the very soft clay. So this picture shows the existing railway station. It's just one platform, and the exit and the entrance is just at both ends of the platform. That's why improve the transport operation and increase safety, and we need to renovate this existing station. So after renovation, the number of platform is increased, and the exit and the entrance also increased as shown here. And also, the existing one is as if it's floating within very soft clay. That's why we need to improve the below of the new station, and also by increasing the number of platform, we'll be able to improve the train traffic. And this picture shows the actual field photos, and land improvement has been done below the existing station. And this is a summary of my lecture, and another 1 minute. And my second lecture is a good shot.